All right, today we're going to talk about sample means, very similar to sample proportions, but now we're talking about means instead of proportions. So in the previous cases, we looked at things like the number of people who said that they believe in ghosts. That makes a proportion. But maybe we asked people to rank their belief on ghosts from 1 to 10, and then we took the average rank of belief of ghosts between all of those people. That would be a sample mean as opposed to a sample proportion. You'll notice that it is very similar to the proportions that we've just talked about. We just have different formulas that we're going to use. So to find the mean of the sampling distribution, sampling meaning if I take a bunch of samples and I put them on a graph, we have a sampling distribution. So I'm really looking for the mean of some x bar because this is a distribution that has a bunch of x bars plotted on it. And this is going to be equal to the true mean mu of the entire population. To find the standard deviation, we're looking really for sigma of x bar. We are taking a bunch of x bars, we've got them on our graph. We're looking for the standard deviation of all of our means. And what you can do here is you take the true population standard deviation and you divide by the square root of n. However, you do still need to check the 10% condition. As always, before we can calculate a standard deviation, and I'll put that on there for you, it's the exact same 10% condition that we've talked about before. We do need our sample size to be less than 10% of our population. This is for the whole independence thing. So you can refer back to when we talked about this. If you know that they're independent or you're sampling with replacement, you don't need to check that 10% condition. All right, let's talk about something. We talked about the 10% condition. It's very similar, but we cannot use the large counts condition for a sample mean. If you recall, the large counts condition was that n times p is greater than or equal to 10, and n times 1 minus p was greater than or equal to 10. Well, if we don't have a p, we don't have a proportion, we can't check this large counts condition, so we need a different condition in order to assume normality. And in this case, for sample means, it's called central limit theorem. I abbreviate this as CLT, and you are welcome to do that as well. The central limit theorem tells us that when n is large, the sampling distribution is approximately normal. So if my sample size is large enough, then my sampling distribution is approximately normal. The large number, the key number here for the central limit theorem is 30. And we'll put that in the next box. So essentially what we're looking for is before we can, run all of the calculations and use our normal distribution and everything like we've done before with our sample proportions, we need to check and see if we have a normal sampling distribution. There are two kind of scenarios that are here. If I know that my population is normal, my sampling distribution is also normal. No need to check the central limit theorem. However, if I don't know if my population is normal, or if I potentially have a non-normal population, the central limit theorem tells us that the sampling distribution of x bar is normal if n is greater than or equal to 30. If we're sampling more than 30 people in each one of our samples for x bar, then the sampling distribution is normal, approximately normal. Let's take a look at this picture. You may recognize this from the website. Remember that this guy up here, this is the population. Anything in blue, those are our sampling distributions, and you can see the blue here on my screen. So this is if I took repeated samples with n equal to 2, and this should really be a lowercase n equal to 2. I know that we use the uppercase n for something special, so don't let that notation kind of confuse you here. This is just taking a sample of 2 people from my population. That does not look normal to me, this first one right here. Now this guy, n equal to 5, this is when I'm taking samples of size 5. That's looking better. I mean, for sure, if we compare it to n equal to 2, n equal to 5 looks a lot better. But this is n equal to 25, definitely looking really good. What I don't understand about this website is they don't allow me the option to choose samples of size 30. I would love to get to 30, but unfortunately that is not a possibility with that website that we've used, so we can get close enough to 25. But you can see at 25, it's really starting to look there approximately normal. And then if we were able to get to 30, we would definitely see a true normal distribution in our sampling distribution. All right, shall we do some examples here? So we have 2 examples. Let's look at this first example 8. So it's telling us about the height of young women. It follows a normal distribution with a mean of 64.5 inches, a standard deviation of 2.5. This is if I was able to take every young woman in the world, find her height, and I calculated the mean and the standard deviation. So what I want to do is I want to answer 2 questions, A and B. And I want to first talk maybe about the difference between these two questions. So for part A, I want to find the probability that a randomly selected young woman is taller than 66.5. The key word here is A. A randomly selected young woman. Let's compare that to B. Find the probability that the mean height of an SRS of 10 young women exceeds 66.5 inches. Same number, same type of question, very similar, but very different things that we're asking. This is where the wording of the questions is really going to come into play here. As we talked about, sample distribution versus a sampling distribution, how those are different. These two questions are asking us two very different things. I'm going to break this up. I'm going to answer part A over here and part B over here so we can compare the two different questions. Okay, so in part A, I have my entire population. I am just going to randomly choose one young woman, and I want the probability that she is taller than 66.5 inches. So let's just worry about that one, and then we'll worry about part B. I know that X, I'm going to call X the height of the person. I know that it's distributed normally, a mean and a standard deviation. And what I'm looking for, what the question in part A is asking me, it's looking for the probability that a single X, one randomly selected woman, is greater than 66.5 inches. This is nothing that we haven't done before. We've been doing this since the beginning of the semester. We're looking for just the probability that one woman picked out of the population is taller than 66.5 inches. So we first want to calculate our z-score. Make sure you sketch your normal curve, plug it into your calculator or use the table, and let's find the probability. I'd like you to pause the video and see if you can fill in all of the parts that you would need, just like we've practiced this in class. See if you can get every piece of the puzzle here, and I'll put my work up on the screen here in just a second. All right, you can check your work against mine. Let's move on to part B. Part B is slightly different. So part B is asking me if I take a simple random sample of 10 young women, what's the probability that the mean height is over 66.5? So honestly, it's okay if a few of the women have heights that are under 66.5. As long as the average of the 10 women exceeds that value, then I'm in the clear and I've met kind of the conditions for part B. So you can see how it's just slightly different here. We do not know now our mean and our standard deviation because now we're taking a simple random sample. So now I need the mu of x bar and sigma of x bar. I need the mean of all of my averages, and I need the standard deviation of all of my averages from all of my different samples. Now we had these formulas at the beginning. I'll put them again for you here. Let's go ahead and find these values here. So I'm saying that the mean of the x bar is the true population mean. That doesn't change. However, the standard deviation will change. And before I can calculate the standard deviation, I do need to check the 10% condition. So that's going to be that n is less than or equal to 1/10 n. And so what I'm going to do is I'll take, all right, well, 10 times my sample of 10, that's 100, and that's definitely less than all women. I guess it says young women, so I'll put the word young, because we're talking about all the young women in the world. So I would feel confident that there's more than 100 young women. Feel all right with that. So let's go ahead and plug in the values. It would be 2.5 for our standard deviation over the square root of 10. That's my sample size. Plug that in your calculator, you should get 0.79. Can I assume normality for this question? Well, we had the two conditions. We said that you either have to know that the population is normal or you need to check the central limit theorem. In this case, we are told that the population is normal. That's good news. So I can assume that my sampling distribution is going to be normal as well. So let's take this same x, my distribution. I know that it's going to be distributed normally. However, this is not x anymore. Now I'm talking about the mean. The average of all of my x values is distributed normally. The mean of my x bar is 64.5, and we did calculate a new standard deviation, 0.79. Now it's exactly the same as what we've done before. Except I guess the only real difference is instead of the probability that x is greater than 66.5, I'm calculating the probability that my x bar, my mean, is greater than 66.5. But other than that, it's exactly the same as on the last page. So I'll have you try this and then maybe plug it in your calculator or use the table and find the probability. This is a lot less common than in part A. In part B, remember we're taking the average. We want the average to be over 66.5. It's about 0.5% chance that this is going to happen, as opposed to the 20% chance that the answer in part A occurred. Different values, different possibilities here. Okay. Make sure that you have the interpretation, and I used very similar interpretation from the wording of the question. The mean height of an SRS of 10 young women being over 66.5 inches. Make sure you have the inches on there. Do you see kind of the difference here between these two types of questions? We're looking at either just plucking one person out of the population or plucking 10 people out of the population and finding the average. And we're kind of looking for two different things here. And that's kind of the difference between a sample distribution in part A and a sampling distribution in part B. We have our 3 steps to success, and we've seen these before. We talked about these before at the end of Unit 4. But let's go ahead and talk about them again. Every time you're answering a question that's going to involve kind of things like this, we're looking for 3 things. Stating the distribution and calculating the values, and that includes the conditions. Then we need to perform all of the calculations and show our work, and then answer the question using that sentence. So what I'm going to do is I am going to put my 3 steps of success here highlighted in different colors. So I'm going to highlight step 1 in green. Stating the distribution, that comes right here where we find our distribution. Calculating the values, that's going to be kind of up here. We didn't have to calculate any values for part A, but I did have to calculate some values for part B, and I did have to check some conditions here for part B. Next thing I need to do is perform the calculations. So that's going to be like finding your z-score. Let's choose a color we haven't seen. We've seen purple on there. Orange is going to, I guess I'll use yellow. I'll do yellow for part 2, perform the calculations. This is going to be actually finding our z-score, writing our probability statement, showing our work. This is all kind of related to showing our work. Performing these calculations, plugging everything in, and showing our work. Then I need to answer the question at hand. And so that's going to be step 3, and that's just my nice little summary statement that I put at the end. And you should kind of think about these 3 steps to success when you are answering any sort of question that's related to these. Okay, so what I want you to do is I want you to try example 9 on your own, and you need to decide if example 9 is more similar to part A of example 8 or more similar to part B of example 8. And think about the 3 different steps to success when you're in, and you don't have to actually write them out, but just think about the 3 steps and make sure that you're including every piece of information that you need here in example 9. All right, so here's my answer for example 9. And I did want to point out, well, I'll give you a second just to check your work, pause the video, and then I want to point something out. I want to point out the wording of my question answer, the sentence at the very end. So essentially what I'm looking at here is I used the notation or kind of the words from this sentence that I just underlined in the question. You plan to budget an average of 1.1 hours per unit to complete the work. So that's where I can see the wording. So the wording of this one is just a little bit different. If you want me to check your wording for this one, you're not sure if you had it right, I'm going to open up a box on the Edpuzzle question here, and you can just type in what you had, and I'm happy to take a look at your answer and kind of see how, if I agree with what you have as your interpretation there at the very end.